In this lesson, you will examine Newton's laws of motion, apply Newton's laws of motion, and investigate concepts such as mass and inertia. The key concepts that we're looking at are the following. Newton's laws of motion, that's Newton's first, second, and third laws. We will look at mass and inertia, and then we will look at acceleration and its relationship to force and mass. Sir Isaac Newton was a great scientist who defined many important laws. We're going to look at his laws of motion, and we're first going to look at Newton's first law of motion. This is defined as a body that will remain in its state of rest or uniform motion in a straight line unless it is acted upon by a net external force. Now let's have a look at that and analyze it. We see that an object at rest will remain at rest unless a resultant force acts on it. Let's have a look at a stationary bus, and it will remain at rest unless the engine is started and it overcomes friction and moves forward. When we look at a moving object that will continue to move at a constant velocity in a straight line unless a resultant force acts on it, let's look at the following. The vehicle will continue at a constant velocity unless we apply brakes, and the vehicle will then stop. We're now going to look at challenge 1 and look at the different types of forces. Firstly, we're going to look at a stationary motorbike, and we want you to name the two forces acting on the bike. A downward and B upward. Question 2 is looking at a car moving at a constant velocity. Remember, constant velocity, there's no acceleration. And we want you to name the four forces and state which of the forces are balanced. So here you're going to look C downwards, D upwards, E in the forward direction that the car is moving, and F in the reverse direction. We suggest that you pause the DVD and do this challenge, and then check the solutions. Let's look at the solutions to challenge 1. Let's hope you got this correct. Write the two forces acting on the bike, on the stationary bike. The force downward is the weight, and the force upward we call the normal force. The second question, remember, it's a constant velocity and there is no acceleration. Therefore, the resultant force is 0. The vertical forces are balanced and the horizontal forces are also balanced. Having a look at the car moving at a constant velocity, we have the weight downward, the normal force upward, and the force of the motor forward, and the frictional force in the reverse direction. Looking at the concepts of mass and inertia. Firstly, what is the definition for mass? Mass is the amount of matter contained by an object. The amount of matter in an object. Inertia is the property of matter which maintains its state of rest or uniform motion in a straight line. We're going to see inertia is therefore the resistance of an object to change its state of motion, and the more mass a body has, the harder it is to change its state of motion. Let's look at that and think about it. Is it easier to catch a tennis ball or a cricket ball? Remember, a cricket ball has more mass than a tennis ball and it's harder. And therefore, is it easier to catch the cricket ball or the tennis ball? Looking at an example of mass and inertia. If a toddler is not properly strapped in a car seat in a car, the toddler will continue to move at the car's velocity when the brakes are applied. An important thing to note is that mass is a scalar quantity. Remember, a scalar quantity has magnitude but no direction. So it has a quantity and it's measured in kilograms, but it does not have a direction. Inertia, however, is a property of matter, and therefore we cannot measure it as such. Now we're going to revise a little bit of grade 10 work on acceleration. The definition for acceleration. Remember, acceleration is the rate of change of velocity. When we see the word rate of change, it is change in velocity over change in time. Therefore, the equation for acceleration is represented as follows. Change in velocity divided by change in time. That gives us acceleration. If we plot a graph of velocity versus time, with velocity on the y-axis and time on the x-axis, one can see in this case where there is a constant velocity, there is no change in velocity. You can see here no change in velocity, therefore delta v will be 0, and the acceleration is therefore 0, and there will be no acceleration. Here we can see a car therefore would be traveling at a constant velocity, a constant value for v. If we plot therefore the acceleration versus time, acceleration on the y-axis and time on the x-axis, one can see therefore the slope of this graph is 0. Remember, acceleration is the change in y over change in x, which is the change in v value divided by the change in time, and therefore there is no acceleration, and the value for a will therefore be 0. If we now plot a graph of velocity versus time with the velocity increasing, starting from the point of origin, the velocity increases positively. You can see here would be a constant change in velocity, and therefore a car would be speeding up. The velocity would be increasing. If we calculate the slope of this graph, which is the change in y value over change in x, you'd see delta v, which is change in velocity, divided by delta t, which is change in time. This would calculate our acceleration value. So the slope of this graph is positive and constant, and therefore this gives us an acceleration value which is positive and is therefore above the axis, the 0 axis, and is constant. So we'd be able to calculate the acceleration for this velocity versus time graph as positive value and constant. We're now going to look at some acceleration relationships, the relationship of acceleration to force and to mass. Firstly, let's look at acceleration against force. If we plot a graph of the acceleration and the resultant force, acceleration on the y-axis and resultant force on the x-axis, and we can see a straight line graph passing through the origin. As the force applied is increased, so the acceleration of the object also increases. Notice both variables increase. As a increases, the value of f increases. So we get a positive slope, and an example of this would be a car speeding up or accelerating as the force of the engine increases. So acceleration increases as the force of the engine increases. This proportion is a direct proportion, so acceleration is therefore directly proportional to force. This is represented in this relationship, acceleration directly proportional to f res. We therefore say a directly proportional graph shows us a straight line graph passing through the origin. We now look at the relationship between acceleration and mass. If we plot a graph of acceleration on the y-axis and mass on the x-axis, we can see that as the mass is increasing this way, you can see the acceleration is decreasing, and we get a graph with this shape. So therefore we see as the mass of the object is increasing, the acceleration of the object is decreasing. One variable increasing, the other variable decreasing. Remember, this is an inverse proportion. So an example of this would be a car that is very heavily loaded with a greater mass will take longer to speed up or accelerate than a lighter, more empty car with a lower mass. So the higher the mass, the lower will be the acceleration. This relationship, if you plot the acceleration on the y-axis versus 1 over the mass, will then give you a straight line graph passing through the origin. This relationship is an inverse proportion, and we see acceleration therefore is inversely proportional to mass. And the relationship is represented as follows: acceleration proportional to 1 divided by mass. This is an inverse proportion. We have examined acceleration being directly proportional to resultant force and indirectly proportional to mass. This is defined in Newton's second law. He said that when a resultant force acts on an object, it causes that object to accelerate in the direction of the resultant force. Now this acceleration is directly proportional to the resultant force and inversely proportional to the mass. We looked at that previously, acceleration being directly proportional to the resultant force and inversely proportional to the mass. These are then combined into this equation. Can you see resultant force equals the mass times acceleration? Here you can see proportion. The resultant force is directly proportional to the acceleration, whereas the acceleration, if you divide through by m, acceleration will therefore be proportional to 1 over m if you use m on this side of the equation. The units for resultant force equals mass times acceleration. Mass is represented in kilograms and acceleration meters per second squared. Remember to write kilogram, the dot in the middle, meter per second squared. Remember, if it's per, it's or divide by, it's -2, and that means acceleration meters per second squared. This unit, kilogram meter seconds to the -2, is a Newton. So a Newton is equivalent to kilogram meter seconds to the -2. This shows the equation F res equals mass times acceleration. And remember, this is Newton's second law. You can define it, if you know the equation, by seeing that the acceleration is directly proportional to the resultant force and inversely proportional to the mass. Now we look at applying Newton's second law. There are certain steps we use in applying Newton's second law, which is represented by resultant force equals mass times acceleration. The first step: determine the forces acting on the object. Draw a force diagram or a free body diagram and label all the forces. Remember to choose a direction as positive. And if there are no forces in the opposite direction of the applied force, then the applied force is the resultant. However, if the applied force is not in the direction of motion, you need to calculate the component of the applied force. And remember to apply F res, resultant force, equals mass times acceleration, in which the resultant force is the sum of the forces acting on the mass. We're now going to look at challenge number 2, and this is applying Newton's second law. An example, a 45 kilogram cyclist rides a bicycle of mass 12 kilograms. He starts by applying a force of 171 newtons. What is his acceleration? And we assume there is no friction. Suggest you pause the DVD and do the calculation. Let us look at the solution to challenge number 2. First, let's consider all the forces acting on the object being the cyclist riding a bicycle. Firstly, weight, represented by the vector W, is the force downwards towards the center of the earth. The normal force balances the weight, and that's the upward force represented by that vector. These forces are balanced forces in the vertical direction. Considering the horizontal direction, we see there is a force applied which gives a motion in the forward direction for the cyclist. And remember, we're considering the situation where there is no friction. So there's no frictional force in the opposite direction. So we're assuming no frictional force, and therefore the only force considered in the horizontal direction is the applied force. So since the forces in the vertical direction are balanced forces, acceleration is only in the horizontal direction, and it's due to the applied force by itself. Since we are considering no friction, we are assuming no frictional force. Therefore, one needs to only consider the applied force in the horizontal direction. We're now going to look at challenge 2 solution with the calculations. The first step is to summarize the given data. Remember to read your question very carefully, underline the keywords, and summarize the data. Here we see the applied force is 171 newtons. The mass, remember, is the mass of the bicycle plus the mass of the rider. So we need the total mass. Mass is 12 kilograms of the bicycle plus 45 kilograms of the rider, and we get a total mass of 57 kilograms. Now remember, the question has asked to calculate acceleration, so we need to look at our data sheet and see which equation we can use. Remember, we have the known applied force and the known variable mass. So we can use the Newton's second law equation. Force equals mass times acceleration. We have applied force as a known variable, the mass as a known variable, and therefore we can calculate the unknown acceleration. Remember, we need to make acceleration, the unknown, as the subject of the formula, since these are the two known values and this is the unknown value. So if we have this equation above from your data sheet, you need to divide the left hand and right hand side of the equation by mass, so we can get acceleration by itself. So we divide force divided by mass, and mass times acceleration divided by mass. The mass would therefore cancel, and we'd have acceleration equals force divided by mass. Step 3 is therefore to substitute your values into your formula, and you get 171 newtons for your force and 57 kilograms for your mass, and therefore we calculate an acceleration for the cyclist and the bicycle 3 meters per second squared. We must write it as follows: 3 meters per second squared. We're now going to look at the concept of components of forces. Firstly, we consider just the horizontal plane when there's one force acting. The applied force therefore equals the resultant force, which equals mass times acceleration. For instance, on a frictionless plane, a box of mass m will accelerate a with an applied force F, And remember, in this case, F will therefore equal F resultant, which equals mass times acceleration. The applied force is in the horizontal plane. Now we're going to consider a force acting at an angle theta to the horizontal. This force has two components. It has a horizontal component and a vertical component. And remember, the angle theta is the distance between this force and the horizontal force, and we can calculate this horizontal force by taking the value of this force in this direction cos of the angle theta. We can calculate the vertical force, F vertical, by multiplying this value F sine of this angle theta. These are the components of this force. So therefore we see if there's one force acting at an angle theta to the horizontal, we can then calculate the component F horizontal by multiplying the force in newtons of this one, cos theta, and the vertical force can be calculated by this value F sine of the angle theta. Now we're going to consider adding frictional force. We were considering a box on a frictionless plane. Now we're going to make sure friction is included in this. If we have an applied force in this direction and a frictional force in the opposite direction, what will happen? Remember, now there's more than one force. So now we're choosing right as positive, and we know the equation that F res equals mass times acceleration. But remember, we need to make sure that this force is the algebraic sum of all the forces in the horizontal plane. And therefore we need to make sure that when we consider this force, it's force minus the friction to give us the algebraic sum of all the forces in the horizontal plane. This will give us the resultant force, which will equal the mass times the acceleration. Let's look at friction and the horizontal components. Now when there's more than one force and a force acting at an angle theta to the horizontal, we need to look at the following. Choosing right as positive, and remember that F equals F resultant equals mass times acceleration, remembering that this F is the algebraic sum of all the forces in the horizontal plane. Remember to include the Fx component. Fx means the horizontal component, or in the x direction, which is the horizontal on a graph. The x-axis is horizontal, and on the vertical axis it is y. So we also refer to the horizontal component as the Fx component, the vertical component as Fy. Looking at the drawing, you can see the following. Consider the box on the table, and we have a frictional force moving in this direction. Remember, we've chosen right as positive, and therefore friction will be a negative value, and so friction can be represented as negative F. Now we need to calculate all the forces in the horizontal plane, and therefore since the applied force is at an angle theta to the horizontal, we can use components of forces to calculate this horizontal component of this applied force. And therefore we use the formula of the horizontal component, or Fx, is equal to F cos of theta. And one can then calculate this Fx value, and remember, to get resultant we need to take the algebraic sum of all the forces in the horizontal plane, and therefore we use Fx plus the negative friction, and therefore it becomes Fx minus friction to get the resultant force in this situation. Let's look at challenge number 3. We're considering horizontal motion, And in both A and B below, find the acceleration of the box if it accelerates only in the horizontal direction. Example A, we're looking at forces acting in a straight line. We have an 11 kilogram box. We have a force of 13 newtons to the left and a force of 55 newtons to the right and a frictional force of 20 newtons to the left. Remember, here we're considering only the horizontal motion, and therefore since there is no vertical motion and there's no applied force at an angle, we don't need to work out components of the forces. Example B, however, is a force acting at an angle. Here we can see a box of mass 15 kilograms and the applied force is 15 newtons at an angle of 60 degrees to the horizontal. Importantly here, you need to work with components of forces. Pause the DVD now and do challenge 3. Looking at challenge 3 and the calculation solutions. Calculation A. We're going to calculate the resultant force. We see that there is a 55 Newton force, applied force to the right, and that is, remember, choosing right as positive. And to the left we have a 20 Newton frictional force and a 13 Newton applied force. Remember, these forces are negative because they're in the opposite direction to the 55. And therefore we see that the force res is 22 newtons. So resultant force is 22 newtons. We look at Newton's equation, F res equals ma, and we need to solve for acceleration. Since acceleration is force divided by mass, we've got the F res equal to 22 newtons. We've calculated it above. And we're going to divide by the mass, which we were given as 11 kilograms. So we've got the applied force as 22 newtons divided by the mass of 11 kilograms, and we can calculate the acceleration to be 2 meters per second squared to the right. This can be written, as you can see, meters per second, which is second squared, so therefore it's negative 2. Meter times seconds to the minus 2. And this is to the right. Calculation B. We know this one is the applied force at an angle 60 degrees to the horizontal. We need to calculate the horizontal component, and therefore we need to say F, which is 15 newtons, cos 60 degrees, and we calculate the F resultant as 7,5 newtons. Now we use F res equals ma and solve for acceleration, which equals force divided by mass, and we know it's 7,5 newtons. Divide by the mass, which was given as 15 kilograms, and we get the acceleration to be 2 meters per second squared to the right. We're now going to look at an inclined plane, or a box on a slope. The inclined plane is at an angle theta to the horizontal. If we examine this box on the slope, we know that it has a force downward equal to its weight, its attraction towards the center of the earth. This is represented by the vector W. Now as the box moves down the slope, if it was frictionless, it would move down the slope with a force parallel or weight to its weight parallel. That component there is a component of this weight vector. We shall have a look at that just now. If there's an upward force of friction on the slope, the force res would be equal to the algebraic sum of all the forces acting in that plane. In other words, if we consider the friction force going up the slope, if there was friction as this box moved down the slope, we would need to take this force and minus the frictional force to get the resultant force. So your resultant force is your algebraic sum of all the forces acting in that plane. Remember, if you take this force as positive, your frictional force will be negative. Now we look at the components of the force weight downwards. There are two components, the weight parallel to the slope and the weight at a 90-degree angle or perpendicular. So we have weight parallel and weight perpendicular. The weight parallel is the red vector, the weight perpendicular is the black vector. This angle theta is the same as the slope angle there, and importantly that we can see this weight perpendicular is the horizontal component and this weight parallel is the vertical component. So we can work out these components if we know the weight. The force perpendicular or weight perpendicular is equal to the weight cos theta. Remember, the horizontal component is cos theta. And the weight parallel or force parallel is equal to weight sine theta. These components you need to be able to work out. Newton's third law. The definition for Newton's third law. When body A exerts a force on body B exerts an equal and opposite force on body A. This is Sir Isaac Newton's third law. For every force there is therefore an equal and opposite force, and remember they act on separate objects. They are also called force pairs. Let's look at an example of Newton's third law. A boy is pushing on a bus. The boy pushes the bus with a force of F1 in that direction. So there's a force of the boy on the bus. Now, according to Newton's law, there's an equal but opposite force of the bus on the boy, and that's F2 in that direction. Importantly, the one force is on the bus that the boy is applying, and the other force is on the boy, which the bus is applying. Now let us consider the motion. The boy is not moving because the frictional force F between his shoes and the ground balances the bus's force on him. And therefore the bus will only move if the force 1 that the boy is applying exceeds the frictional force between the bus's tires and the ground. And if the boy's force is greater, F1 is greater than that frictional force, he will be able to move the bus forward, and the bus would move. Now remember, in Newton's third law, it is on separate objects. So the boy is applying the force on the bus, and the bus is applying a force on the boy. Let's do challenge number 4, which is applying Newton's third law. Identify the force pairs acting on the horse and cart. Let's pause the DVD now and do this challenge. The solutions for challenge 4. The first force pair is a force of the horse on the cart and the cart on the horse. There's a force of the ground on the horse and the force of the horse on the ground. We're going to conclude this DVD with a summary of the formulae and the definitions required. Relationships with acceleration. Acceleration is directly proportional to the resultant force and indirectly proportional to the mass, 1 divided by mass. The resultant force. The resultant force is the algebraic sum of all the forces acting on the object. So resultant force equals mass times acceleration. Remember, this is Newton's second law. We often have to calculate components of a force. Remember, when a force is applied at an angle theta to the horizontal, it contains two components. The horizontal component, which can be worked out by F cos theta, and the vertical component, which is F sine theta. The F horizontal component is the X component, and the F vertical is the Y component. A way to remember that horizontal component is cos and vertical is sine is to remember that horizontal with an O and cos with an O, and vertical has an I and sine has an I. And it's important to not mix these two up. A summary of the definitions. Firstly, mass. Mass is the amount of matter contained by an object, and inertia is the property of matter which maintains its state of rest or uniform motion in a straight line.